At 4 a.m. on March 28, 1979, Unit 2 of the 3 Mile Island Nuclear Generating Station operated according to its fundamental design philosophy, a pressurized water reactor system, where the pressurizer served as both pressure control mechanism and primary indication of reactor coolant system inventory. This design premise, embedded in every training manual and emergency procedure, established pressurizer water level as the definitive indicator of adequate core cooling. For nearly 6 years of operation, this assumption had proven reliable under all tested conditions. The pressurized water reactor design represents a triumph of engineering systematization. Primary coolant circulates through the reactor core at approximately 600 degrees Fahrenheit under 2,155 pounds per square inch of pressure, preventing boiling while maximizing heat transfer efficiency. The pressurizer, a vertical cylindrical vessel connected to the primary loop hot leg, maintains system pressure through a steam bubble in its upper section and provides operators with water level indication that had never failed to correlate with adequate core inventory. This correlation formed the foundation of operator mental models and emergency response procedures. Rising pressurizer level indicated increasing primary system inventory and, by extension, adequate core cooling. Falling levels suggested inventory loss and potential core exposure. The logic appeared unassailable. If the pressurizer contained water, the primary system contained sufficient coolant to cover the reactor core. Training reinforced this understanding through hundreds of simulator exercises where pressurizer level consistently predicted core cooling adequacy. The design assumptions underlying this indicator system reflected the best engineering understanding of single-phase liquid behavior in pressurized systems. Under normal operating conditions and most anticipated transients, primary coolant remains in liquid form throughout the reactor coolant system. The pressurizer level instrument, a differential pressure measurement between the bottom and a reference level in the pressurizer, accurately reflects liquid inventory under these conditions. Temperature and pressure instrumentation confirmed that design basis assumptions held. Hot leg temperatures of 606 degrees Fahrenheit and pressures above 2,000 psia ensured subcooled liquid conditions throughout the primary system. However, the design contained an unrecognized vulnerability that would prove catastrophic under specific thermal hydraulic conditions. The pressurizer level indication system assumed single-phase liquid conditions throughout the primary system. When two-phase flow conditions developed, with steam voids forming in the reactor vessel and primary piping, the relationship between pressurizer level and actual core cooling became not merely inaccurate, but systematically misleading. This vulnerability remained hidden within the physics of two-phase flow behavior. As primary system pressure decreases below saturation conditions, coolant begins to flash to steam within the reactor vessel and hot leg piping. These steam voids, being less dense than liquid water, cause the liquid level in the pressurizer to rise even as actual liquid inventory in the primary system decreases. The pressurizer level instrument, measuring differential pressure across liquid columns, cannot distinguish between inventory increases from external addition and apparent increases from voiding-induced level changes. The control room interface provided no mechanism for operators to recognize when design assumptions had become invalid. No direct indication of core water level existed. No instruments measured void fraction in the primary system. No alarms warned that pressurizer level readings had transitioned from accurate inventory indication to misleading artifact of two-phase flow conditions. The same instrument that had reliably indicated adequate cooling for 6 years of operation would indicate rising inventory, while the reactor core progressively uncovered. Training programs developed around design basis scenarios reinforced operator reliance on pressurizer level indication. Emergency procedures directed operators to maintain pressurizer level within specified bands to ensure adequate core cooling. Simulator exercises consistently demonstrated the correlation between level control and plant safety. No scenario had trained operators to question the validity of pressurizer level readings or to recognize conditions where this primary diagnostic tool became unreliable. The procedural structure reflected this design philosophy through its hierarchy of safety actions. Loss of coolant accident procedures prioritized maintaining pressurizer level through emergency core cooling system activation. Operators learned to increase emergency cooling flow when level decreased and reduce flow when level approached upper limits to prevent water-solid conditions in the pressurizer. These procedures, logical within the framework of single-phase flow assumptions, would prove counterproductive under two-phase conditions where reducing cooling flow would accelerate core uncovery. Technical specifications reinforced operator focus on pressurizer level as the primary safety indicator. Level instrumentation requirements exceeded those for any other single parameter, reflecting its perceived importance for safe operation. Redundant level measurement systems provided backup indication, but all measured the same physical phenomenon and shared the same fundamental assumption about single-phase liquid conditions. Multiple independent instruments would provide consistently misleading information under two-phase flow conditions, creating false confidence in readings that no longer reflected physical reality. The regulatory framework governing reactor design had not anticipated scenarios where primary safety instrumentation could provide systematically false information while remaining technically functional. Design basis accidents assumed either clear functional failures of instrumentation systems or retention of instrument validity throughout accident progression. The possibility that instruments could continue operating within technical specifications while providing diagnostically invalid information had not been incorporated into design requirements or operator training programs. Engineering analysis supporting the original design had focused on instrument accuracy under normal and anticipated abnormal conditions. Pressurizer level measurement systems met all accuracy requirements for their intended function of inventory control during planned operational transients. The analysis did not address diagnostic validity under severe accident conditions involving two-phase flow throughout the primary system, as such conditions exceeded the design basis scope for commercial reactor licensing. This gap between design assumptions and physical reality created what would later be recognized as a systematic vulnerability in pressurized water reactor design. The most trusted instrument in the control room, supported by the most comprehensive training and procedures, would provide information that was instrumentally accurate but operationally catastrophic. Operators following established procedures and trusting validated instrumentation would make decisions that appeared correct within their training but accelerated core damage in the actual physical system. The 3 Mile Island Unit 2 control room on March 28, 1979, represented the culmination of 1950s nuclear engineering philosophy, instrument-centered control systems supported by procedure-based operator actions. This philosophy assumed that accurate instruments, comprehensive procedures, and well-trained operators would provide sufficient safety margins for all credible accident scenarios. The design had not anticipated conditions where the fundamental assumptions underlying primary safety instrumentation would become invalid without any indication to the operators responsible for plant safety. These design assumptions would be tested within hours by a sequence of equipment failures that created precisely the thermal hydraulic conditions where pressurizer level indication became misleading. The subsequent operator actions, logical within their training and supported by their most trusted instruments, would demonstrate how engineering assumptions embedded within safety systems could transform a manageable equipment failure into an unprecedented reactor accident. The 3 Mile Island Unit 2 control room represented the state of nuclear plant human-machine interface design circa 1974, when construction began. Banks of analog indicators, hundreds of alarm lights, and strip chart recorders provided operators with what designers believed to be comprehensive plant status information. This interface philosophy assumed that trained operators could effectively process simultaneous information from multiple systems during emergency conditions. The events of March 28, 1979, would reveal critical weaknesses in this assumption. The alarm system design reflected 1970s understanding of information management during abnormal conditions. Approximately 1,600 alarm points monitored various plant parameters, with visual annunciator panels and an alarm typewriter providing indication when predetermined set points were exceeded. The system prioritized comprehensiveness over clarity, assuming that more information would enhance operator decision-making capability during emergencies. No hierarchy distinguished between critical safety alarms and less significant operational warnings. Within the first few minutes of the March 28 event, over 100 alarms activated simultaneously as automatic systems responded to the initiating transient. The alarm typewriter designed to print sequential messages could not keep pace with the alarm rate and began printing with significant delays. Audible alarm horns created a cacophony that made verbal communication difficult among control room personnel. The annunciator panels, designed with individual lights for each alarm, presented a wall of flashing indicators that provided no guidance for prioritization or systematic response. This alarm flood created immediate information overload for operators trained to rely on systematic alarm response procedures. Normal practice involved acknowledging each alarm individually, determining its cause, and taking appropriate corrective action before proceeding to the next indication. The simultaneous activation of systems throughout the plant made this methodical approach impossible, forcing operators to make rapid decisions based on incomplete information while managing continuing alarm inputs. The procedural structure governing emergency response had evolved from military and aerospace operational philosophy, emphasizing strict adherence to written guidance under abnormal conditions. Emergency operating procedures provided step-by-step instructions for responding to specific initiating events, assuming that operators could correctly diagnose the type of emergency in progress. However, the procedures were designed around single failure scenarios and did not address complex multi-system events where symptoms might indicate multiple simultaneous problems. Two fundamental procedural approaches competed for operator attention during the early phases of the accident: event-based procedures that responded to specific equipment failures, and symptom-based procedures that addressed abnormal plant conditions regardless of cause. The reactor trip and safety injection actuation triggered event-based procedures designed to manage reactor shutdown and ensure adequate core cooling. Simultaneously, rising pressurizer level and other symptoms suggested application of procedures designed to prevent pressurizer, water, to solid conditions, and steam generator overfill. Training had emphasized the dangers of pressurizer overfill scenarios, where excessive emergency core cooling injection could create water-solid conditions leading to potential overpressurization of the primary system. Instructors repeatedly stressed that operators must carefully control emergency core cooling flow to prevent this condition, which could challenge primary system integrity. This training emphasis reflected lessons learned from earlier reactor designs where overfill events had caused significant problems. The specific training focus on preventing overfill created a cognitive bias toward reducing emergency core cooling flow when pressurizer level approached upper limits. Operators had practiced this response hundreds of times in simulator training, where excessive cooling injection consistently led to undesirable plant conditions. The training scenarios reinforce the principle that operators must actively manage emergency systems rather than allowing them to operate automatically without supervision. However, the training program had not adequately addressed loss of coolant accident scenarios where apparent pressurizer level increases resulted from two-phase flow conditions rather than actual inventory increases. Simulator models used for training did not accurately represent severe accident thermal hydraulics, limiting operator exposure to scenarios where trusted instruments provided misleading information. The training assumption that instruments would provide accurate diagnostic information throughout all credible accident scenarios proved invalid under actual accident conditions. Organizational factors within the utility's operating structure influenced decision-making patterns during the emergency. Shift crews were trained to operate independently during normal conditions, but to seek guidance from engineering, support personnel during significant abnormal events. However, the communication systems and procedures for obtaining technical support had not been designed for rapidly evolving accident conditions where minute-by-minute decisions could affect core safety. The maintenance status of critical equipment introduced additional latent vulnerabilities into the plant configuration. The pilot-operated relief valve position indication system had been experiencing intermittent failures, providing unreliable information about valve status during previous operations. Maintenance personnel had noted these problems but had not implemented definitive repairs, leaving operators with uncertainties about the actual position of this critical valve during the accident sequence. The auxiliary feedwater system isolation valves had been closed for planned maintenance activities, removing an important backup cooling capability for the steam generators. While this maintenance was conducted within technical specification requirements, it eliminated a defense in-depth capability that might have mitigated the consequences of the primary system failure. The configuration management system tracked individual component availability but did not assess cumulative effects of multiple equipment outages on overall safety margins. Work control processes governing maintenance activities focused on individual system impacts rather than integrated plant vulnerability assessments. Maintenance scheduling prioritized equipment availability for power generation rather than optimization of safety system redundancy during planned outages. This approach, standard throughout the nuclear industry during the 1970s, assumed that technical specification compliance provided adequate safety margins regardless of specific equipment combinations that might be unavailable simultaneously. The control room staffing model reflected assumptions about operator workload distribution during emergency conditions. 2 licensed operators, a control room supervisor and a reactor operator, shared responsibility for monitoring all plant systems and implementing emergency procedures. This staffing level, adequate for normal operations and simple transients, proved insufficient for managing complex multi-system failures requiring simultaneous attention to reactor coolant system behavior, steam generator conditions, electrical system status, and containment parameters. Communication protocols among shift personnel assumed that normal chain-of-command structures would remain effective during emergency conditions. However, the rapid pace of event progression and high stress levels degraded normal communication effectiveness. Multiple conversations occurred simultaneously as different operators attempted to understand various system behaviors, making coordination of overall response strategy difficult. The shift supervisor faced competing demands for immediate decisions while lacking complete information about plant status. Emergency procedures required authorization from licensed personnel before implementing certain actions, but the procedures did not address scenarios where multiple emergency actions might be required simultaneously. The decision-making framework assumed sequential rather than parallel emergency responses, creating procedural conflicts when multiple systems required immediate attention. These latent conditions, alarm system overload, competing procedures, training biases, maintenance configurations, staffing limitations, and communication challenges, existed independently without apparent safety significance. However, the combination of these factors during a complex accident scenario created conditions where well-trained operators following established procedures would make decisions that appeared logical within their understanding, but proved counterproductive for maintaining core cooling. The human factors environment at 3 Mile Island Unit 2 reflected industry-standard practices for nuclear plant design and operation during the 1970s. The accumulation of latent vulnerabilities within this environment had not been recognized or addressed through systematic analysis. Each individual element, training emphasis, procedural structure, alarm design, staffing model, met regulatory requirements and industry standards, yet their interaction under accident conditions would prove inadequate for preventing core damage. At 4:36 a.m. on March 28, 1979, a routine maintenance error in the plant's condensate polishing system triggered a sequence of automatic responses that should have represented a minor operational upset. The condensate polisher resin transfer system experienced a malfunction that caused closure of feedwater block valves, stopping the flow of feedwater to both steam generators. This type of transient, while unplanned, fell well within the design envelope for automatic plant protection systems. Within 8 seconds of the feedwater interruption, reactor power began increasing as steam generator water levels dropped and heat removal decreased. The reactor protection system, monitoring multiple plant parameters simultaneously, detected the deviation from normal conditions and initiated an automatic reactor scram at 4:37 a.m. Control rods inserted into the reactor core within 1.2 seconds, terminating the nuclear chain reaction as designed. Steam generator pressure began rising as heat input from the primary system continued while steam demand from the turbine decreased. The turbine generator automatically tripped offline as designed when the reactor scrammed, eliminating the normal heatsink for steam generator output. Primary system pressure began rising as heat generation continued from radioactive decay in the reactor core, approximately 6% of full power thermal output, while normal heat removal through the steam generators was disrupted. The pressurizer pressure relief system activated automatically when primary system pressure reached 2,255 psia, with the pilot-operated relief valve opening to discharge excess coolant and reduce system pressure. These automatic responses represented exactly the type of defense-in-depth operation for which the plant had been designed. No immediate operator action was required. The plant protection systems had successfully prevented any challenge to safety limits. Operators observed the automatic responses and began implementing post-reactor trip procedures, which emphasized restoring normal heat removal pathways and maintaining primary system parameters within acceptable ranges. However, within this apparently normal sequence, a critical failure was developing that would not be recognized for several hours. The pilot-operated relief valve, which had opened to relieve excess pressure during the initial transient, failed to reclose when system pressure decreased below its set point. The valve remained in the open position, creating a loss of coolant accident through an 2.2-inch diameter flow path that would drain approximately 32,000 gallons of primary coolant over the next 2 hours. The control room indication system provided ambiguous information about the pilot-operated relief valve status. The position indicator light, which should have confirmed valve closure, was actually wired to indicate the status of the solenoid valve that controlled air supply to the relief valve operator, not the actual valve position. This design choice, common in 1970s nuclear plant instrumentation philosophy, provided information about the control signal sent to the valve rather than confirmation of valve response to that signal. The indicator light showed that the control system had commanded valve closure, leading operators to assume the valve had actually closed. This instrumentation design flaw created the first critical divergence between control room indication and actual plant status. While operators believed they were managing a routine post-trip transient with intact primary system boundary, they were actually responding to a small break loss of coolant accident with continuing inventory loss. The primary system was slowly depressurizing as coolant discharged through the stuck-open relief valve, but this depressurization appeared consistent with normal post-trip cooldown procedures. Auxiliary feedwater systems should have provided backup cooling to the steam generators, maintaining secondary side heat removal capability during the transient. However, maintenance activities had left isolation valves closed in the auxiliary feedwater supply lines to both steam generators. This configuration, while permitted under technical specifications, eliminated the automatic backup for normal feedwater supply just when it was most needed. The auxiliary feedwater pumps started as designed, but no water could reach the steam generators through the closed isolation valves. Operators did not initially recognize the auxiliary feedwater isolation because the pump start indications suggested the system was functioning normally. Flow indicators and pump status lights provided the expected indications for system startup, but actual flow measurement instrumentation was not prominently displayed in the main control panels. The design assumption that pump operation indicated successful flow delivery proved incorrect when isolation valves prevented water from reaching its intended destination. The combination of continuing primary coolant loss through the stuck-open relief valve and lack of secondary side cooling through the auxiliary feedwater system created conditions that exceeded the analyzed design basis for plant emergency procedures. Operators were simultaneously managing what appeared to be a routine reactor trip, while actually dealing with a loss of coolant accident, complicated by loss of secondary heat removal. Neither condition alone represented an immediate threat to core safety, but their combination created a scenario not adequately addressed in existing emergency procedures. Primary system pressure continued decreasing as coolant discharged through the relief valve, eventually dropping below the set point for automatic safety injection system actuation at approximately 1,600 psia. High-head safety injection pumps started automatically and began injecting borated water into the primary system to replace lost inventory and ensure adequate core cooling. This automatic response represented another layer of defense-in-depth protection, activating without operator intervention when predetermined conditions were reached. However, the safety injection system actuation created immediate concerns among control room operators who had been trained to prevent unnecessary activation of this system. Emergency procedures emphasized that inadvertent safety injection could lead to excessive primary system inventory, potentially causing pressurizer overfill and subsequent challenges to primary system integrity. The safety injection actuation appeared unnecessary given the apparently stable post-trip conditions indicated by control room instrumentation. The pressurizer level indication reinforced operator concerns about excessive emergency core cooling injection. As safety injection pumps added borated water to the primary system, pressurizer level began rising toward upper limits. This indication suggested that the automatic safety injection was providing more cooling water than needed to maintain adequate core cooling, consistent with training scenarios where operators were required to terminate unnecessary safety injection to prevent overfill conditions. At this critical decision point, operator mental models formed during training began conflicting with actual physical conditions in the reactor vessel. The rising pressurizer level, which operators interpreted as evidence of adequate and potentially excessive primary system inventory, was actually the result of voiding in the reactor vessel and primary piping caused by continued depressurization from the stuck-open relief valve. Steam formation in the reactor vessel displaced liquid coolant, causing apparent inventory increases in the pressurizer while actual liquid inventory covering the reactor core decreased. Operators could not recognize this physical transformation because no instrumentation provided direct indication of void formation or core liquid level. The pressurizer level instrument, their primary diagnostic tool for assessing core cooling adequacy, indicated rising inventory that appeared to confirm adequate core cooling. Temperature and pressure measurements remained within expected ranges for post-trip conditions. No alarms warned that design assumptions underlying primary instrumentation had become invalid. The decision to reduce safety injection flow appeared logical within the framework of operator training and available instrumentation. Emergency procedures provided guidance for terminating safety injection when pressurizer level approached upper limits, specifically to prevent overfill conditions that could challenge primary system integrity. The procedures assumed that pressurizer level accurately reflected primary system inventory under all conditions, an assumption that had proven reliable throughout previous plant operations. This decision marked the critical transition from a manageable equipment failure to an unrecoverable accident sequence. By reducing emergency core cooling injection, while coolant continued to discharge through the stuck open relief valve, operators unknowingly accelerated the approach to core uncovery conditions. The same instrumentation and procedures that had provided safety margins during previous transients now guided operators toward actions that worsened the physical situation in the reactor vessel. The time-critical nature of this decision process prevented comprehensive analysis of all available information. Multiple alarms and system responses demanded immediate attention, while operators attempted to understand the overall plant condition and select appropriate response strategies. The apparent stability of most plant parameters suggested that conservative emergency response actions were not warranted, supporting decisions to moderate automatic safety system responses, rather than allowing them to operate at maximum capacity. By 5 a.m., approximately 1 hour after the initiating event, the 3 Mile Island Unit 2 reactor had transitioned from a manageable post-trip transient to an unrecognized loss of coolant accident, with continuing core cooling degradation. The pilot-operated relief valve remained stuck in the open position, discharging primary coolant at a rate of approximately 220 gallons per minute through a flow path that operators believed had been isolated. This hidden coolant loss would ultimately drain more than 32,000 gallons from the primary system over the next 2 hours. The relief valve failure mechanism represented a common mode vulnerability in pilot-operated relief valve designs of this era. The valve consisted of a main relief valve controlled by a smaller pilot valve, which directed air pressure to open and close the main valve disc. When system pressure exceeded the set point, the pilot valve opened, allowing air pressure to lift the main valve disc and permit coolant discharge. Upon pressure reduction below the set point, the pilot valve should have closed, venting air pressure and allowing the main valve disc to reseat under spring force and system pressure. However, foreign material or mechanical damage had prevented the main valve disc from properly seating when the pilot valve closed. The valve remained approximately 70% open, creating a flow area equivalent to a 2.2-inch diameter opening in the primary system pressure boundary. This opening provided a direct flow path from the pressurizer through the relief valve to the pressurizer relief tank in the reactor auxiliary building, effectively creating a small break loss of coolant accident. The pressurizer relief tank, designed to accommodate brief pressure relief valve discharges, began receiving continuous coolant flow that exceeded its design capacity. Temperature and pressure in the relief tank increased rapidly as hot primary coolant discharged into the tank. Within approximately 15 minutes, the tank's rupture disc activated as designed, providing a relief path for the excessive inventory and pressure, but also creating a pathway for radioactive coolant to enter the reactor auxiliary building atmosphere. Evidence of relief tank overpressurization was available to control room operators through relief tank temperature and pressure instrumentation, but this information was not prominently displayed on main control panels and was not specifically addressed in post-trip emergency procedures. The temperature indication suggested unusual conditions in the relief tank system, but operators focused on more prominent indications related to reactor coolant system and steam generator parameters during the complex multi-system response requirements. Primary system depressurization continued as coolant discharged through the relief valve, eventually reaching pressure levels where saturation temperature approached the actual coolant temperature in portions of the reactor vessel and primary piping. When system pressure dropped below approximately 1000 psia, coolant began flashing to steam in regions of the reactor vessel where temperature remained near 600 degrees Fahrenheit. This steam formation marked the critical transition from single-phase liquid conditions to two-phase flow throughout portions of the primary system. The onset of two-phase flow fundamentally altered the relationship between pressurizer level indication and actual core cooling adequacy. Steam bubbles forming in the reactor vessel and hot leg piping displaced liquid coolant, forcing liquid levels higher in connected systems, including the pressurizer. The pressurizer level transmitter, measuring differential pressure across liquid columns, interpreted this liquid displacement as inventory increase even though actual liquid inventory in the primary system continued decreasing through the relief valve discharge. Core thermocouple instrumentation began indicating temperatures exceeding normal operating ranges as liquid coolant levels in the reactor vessel dropped below the tops of the fuel assemblies. Exit thermocouples measuring coolant temperature leaving the reactor core showed readings approaching saturation temperature for the decreasing system pressure, indicating that liquid coolant was boiling as it passed through the core. However, these readings were not immediately recognized as evidence of core uncovery, because they remained consistent with expected behavior during depressurization transients. Neutron flux instrumentation confirmed that the reactor remained subcritical with control rods fully inserted, eliminating nuclear heating as a contributor to rising core temperatures. The temperature increases observed on core thermocouples resulted from decay heat removal being compromised by decreasing liquid coolant inventory and increasing void formation in the core region. Approximately 6% of full power thermal output continued from radioactive decay of fission products, requiring continuous cooling to prevent fuel damage. The emergency core cooling system, partially throttled by operator actions to control pressurizer level, could not provide sufficient makeup flow to compensate for the continuing loss through the relief valve while maintaining liquid inventory in the reactor vessel. High-head safety injection pumps delivered approximately 150 gallons per minute of borated water to the reactor vessel, but this flow rate was insufficient to offset the 220 gallon per minute loss through the relief valve, while also replacing inventory lost to steam formation in the core region. Mass balance calculations, which were not performed in real time but would later be reconstructed from plant data, demonstrated that the reactor vessel was slowly losing liquid inventory despite apparent pressurizer level increases. The primary system contained approximately 36,000 gallons of coolant under normal conditions, with roughly 12,000 gallons in the reactor vessel itself. Continued discharge through the relief valve, combined with steam formation displacing liquid in the vessel, gradually reduced liquid coverage over the reactor core. By approximately 6 a.m., 2 hours after the initiating event, core thermocouples indicated temperatures exceeding 700 degrees Fahrenheit, well above saturation temperature for the existing system pressure of approximately 1,000 psia. These temperatures provided definitive evidence that steam, rather than liquid coolant, surrounded the upper portions of the fuel assemblies. However, operators interpreted these readings as consistent with natural circulation establishment during post-trip cooldown, rather than evidence of core uncovery progression. The point of no return for preventing significant fuel damage occurred when liquid coolant levels dropped below the top of the active fuel region, approximately 8 feet above the bottom of the reactor vessel. Once uncovered, fuel rod cladding temperatures began increasing rapidly due to decay heat generation without adequate cooling. Zircaloy cladding surrounding the uranium fuel pellets experienced temperature excursions that initiated oxidation reactions with steam, generating hydrogen gas and additional heat. Steam zircaloy reaction became self-sustaining once cladding temperatures exceeded approximately 1,800 degrees, creating an autocatalytic process where reaction heat accelerated further temperature increases. This chemical reaction, not anticipated in operator training or emergency procedures, generated significant quantities of hydrogen that would later create additional safety challenges. The reaction also consumed steam that might otherwise have provided some cooling capability for the uncovered fuel assemblies. Core damage progression accelerated as more fuel assemblies became uncovered and cladding temperatures exceeded metallurgical limits for zircaloy. Fuel pellet geometry began changing as temperatures approached the melting point of uranium dioxide, approximately 5,100 degrees. However, the full extent of core damage would not be recognized for several hours because primary indicators available to operators, pressurizer level, pressure, and temperature, continued suggesting manageable conditions despite the physical destruction occurring in the reactor vessel. The feedback loop between operator actions and core damage became established as efforts to control pressurizer level continued reducing emergency core cooling injection. Each reduction in safety injection flow decreased the rate of inventory makeup to the reactor vessel, while coolant loss through the relief valve continued unchanged. These actions, logical within the framework of pressurizer level control, systematically reduced the liquid inventory available for core cooling, while operators believed they were preventing overfill conditions. Radiation monitoring systems began detecting elevated activity levels in the reactor coolant system and containment atmosphere as fuel cladding failed and released fission products into the primary coolant. However, these indications developed gradually and were not immediately recognized as evidence of fuel damage because some radioactivity release was expected during any transient involving primary system heating or cooldown. The magnitude and composition of the radioactivity would later confirm extensive fuel damage, but this information was not available to operators during the critical decision-to-making period. The 3 Mile Island Unit 2 reactor core had sustained damage to approximately 45% of its fuel assemblies by 7 a.m., 3 hours after the initiating feedwater transient. This damage occurred while operators followed established emergency procedures and relied on their primary safety instrumentation, demonstrating how design assumptions embedded in safety systems could lead trained operators to take actions that accelerated rather than prevented core damage progression. At approximately 6:18 a.m. on March 20th, nearly 2.5 hours after the initiating event, 3 Mile Island Unit 2 operators finally recognized that the pilot-operated relief valve had remained open throughout the transient. A reactor operator noticed that temperatures in the discharge line downstream of the relief valve remained elevated, indicating continuing flow through a valve that should have been closed. This discovery fundamentally changed operator understanding of plant conditions and initiated efforts to isolate the continuing coolant loss that had driven the accident progression. The relief valve isolation was accomplished by closing a motor-operated block valve upstream of the pilot-operated relief valve, effectively stopping the primary coolant discharge that had been occurring for over 2 hours. This action eliminated the driving force behind the loss of coolant accident and should have enabled recovery of primary system inventory through continued emergency core cooling injection. However, the damage to the reactor core had already been extensive, and new challenges emerged as operators attempted to establish stable cooling conditions. Recognition of the relief valve problem initiated a reassessment of primary system conditions and emergency response strategies. Operators realized that their previous efforts to limit emergency core cooling injection had been counterproductive, allowing continued inventory loss while restricting makeup flow. Emergency procedures were revised to prioritize maximum cooling injection to recover primary system inventory and ensure adequate core cooling, representing a fundamental shift from previous concerns about preventing overfill conditions. However, the transition to aggressive cooling injection revealed new complications arising from the physical conditions that had developed in the reactor vessel during the period of core uncovery. The combination of high temperatures, steam formation, and potential hydrogen generation from steam zircaloy reactions had created thermal and chemical conditions not addressed in existing emergency procedures. Establishing reliable core cooling would prove more complex than simply restoring primary system inventory. Natural circulation establishment became a critical concern as operators attempted to verify that cooling flow was reaching all regions of the reactor core. Natural circulation relies on density differences between hot and cold water to drive flow through the reactor coolant system without requiring reactor coolant pump operation. However, the presence of steam voids in the reactor vessel and primary piping could interrupt circulation patterns and create regions where decay heat removal remained inadequate, despite overall system pressure and inventory recovery. Reactor coolant pump operation, normally used to ensure positive circulation during all plant conditions, became problematic due to concerns about pump damage from operating in two-phase flow conditions. Steam voids in the reactor vessel could cause pump cavitation and mechanical damage if pumps were operated before adequate liquid inventory was restored. However, without forced circulation, operators could not confirm that cooling flow was reaching all portions of the reactor core, particularly regions that might be surrounded by steam voids. Core exit thermocouple readings continued showing elevated temperatures even after relief valve isolation, suggesting that adequate cooling had not been immediately restored to all fuel assemblies. Some thermocouples indicated temperatures exceeding 2,000 degrees, well above normal operating ranges and approaching levels where fuel damage progression could continue even without nuclear heating. These readings provided evidence that core cooling challenges persisted despite operator efforts to restore normal primary system conditions. The most significant secondary crisis emerged from hydrogen generation during the period of core damage. Steam zircaloy reactions occurring when fuel cladding temperatures exceeded metallurgical limits had produced substantial quantities of hydrogen gas that accumulated in the upper regions of the reactor vessel and primary system piping. This hydrogen posed multiple challenges for plant recovery and long-term safety that had not been anticipated in emergency procedures. Hydrogen accumulation in the reactor vessel head created the potential for gas binding that could prevent natural circulation establishment even after liquid inventory was restored. Gas-bound conditions would isolate portions of the reactor core from cooling flow, potentially leading to continued temperature increases and additional fuel damage. However, no procedures existed for managing gas-bound conditions in the reactor vessel, and instrumentation provided limited information about gas distribution throughout the primary system. The possibility of hydrogen combustion or explosion within the containment structure became a significant concern as hydrogen generated in the reactor vessel was transported through the primary system to the containment atmosphere through relief valve discharge and other leak paths. Hydrogen concentrations approaching combustible limits could create the potential for rapid pressure increases that might challenge containment integrity, representing an entirely different category of safety concern from the original core cooling challenges. Radiation monitoring throughout the plant indicated substantially elevated activity levels as fission products released during fuel damage circulated through the primary system and escaped to the containment atmosphere. These radiation levels complicated access for manual operations and monitoring activities while confirming that significant fuel damage had occurred. However, the extent of fuel damage could not be accurately assessed from radiation measurements alone, leaving operators uncertain about the actual core condition. Efforts to establish stable plant conditions were further complicated by uncertainties about primary system integrity following the thermal and pressure transients experienced during the accident. Components throughout the reactor coolant system had experienced temperature and pressure cycles outside normal operating ranges, potentially affecting their structural reliability. Steam generator tube integrity became a particular concern, as failure of these boundaries could provide pathways for radioactive material release to the secondary system and ultimately to the environment. The auxiliary feedwater isolation valves that had contributed to the accident progression were finally opened approximately 8 hours after the initiating event, restoring secondary side cooling capability to the steam generators. This action enabled heat removal through the steam generators and reduced dependence on primary system cooling alone for decay heat removal. However, the delay in recognizing and correcting this configuration had eliminated a critical backup cooling capability during the most severe phase of the accident. Emergency response coordination became increasingly complex as the scope and severity of the accident became apparent to plant management and utility executives. Notifications to regulatory authorities and emergency response organizations initiated off-site support activities, while control room operators continued managing immediate plant stabilization efforts. The interface between immediate operational decisions and longer-term recovery planning created additional coordination challenges during an already stressful situation. Attempts to quantify the extent of core damage were limited by instrumentation capabilities and the unprecedented nature of the accident conditions. Core exit thermocouples provided temperature information but could not directly measure fuel geometry changes or the extent of cladding failure. Radiation measurements confirmed fission product release, but could not determine whether fuel melting had occurred or how much of the core remained in normal geometric configuration. The development of effective recovery strategies required understanding of physical conditions in the reactor vessel that exceeded the scope of existing instrumentation and emergency procedures. Questions about hydrogen distribution, core geometry, natural circulation capability, and fuel cooling effectiveness would require engineering analysis and potentially innovative approaches not addressed in standard emergency operating procedures. The transition from immediate emergency response to long-term recovery planning highlighted gaps between existing procedures and the realities of severe accident management. By the end of March 28, approximately 20 hours after the initiating event, 3 Mile Island Unit 2 had achieved a quasi-stable condition with the reactor's subcritical primary system pressure and inventory restored and decay heat removal established through both primary and secondary cooling systems. However, significant uncertainties remained about core condition, hydrogen management, and long-term plant integrity that would require weeks of additional analysis and recovery operations to fully resolve. The forensic investigation of 3 Mile Island Unit 2 began within days of the accident but would continue for more than a decade, as investigators worked to understand the physical conditions that had developed in the reactor vessel and the systematic failures that had enabled core damage to occur. Initial assessments, based on available instrumentation and radiation measurements, suggested significant fuel damage but could not determine the extent of core geometry changes or the actual distribution of damaged and intact fuel assemblies within the reactor vessel. Early attempts to establish the scope of core damage relied primarily on analysis of fission product releases to the primary coolant and containment atmosphere. The composition and quantity of radioactive isotopes detected in coolant samples and atmospheric monitoring indicated that substantial fuel cladding failure had occurred, with some evidence suggesting that fuel melting might have taken place. However, the relationship between measured radioactivity and actual core damage remained uncertain without direct visual confirmation of fuel assembly conditions. The first definitive evidence of extensive core damage came from reactor vessel head removal operations conducted in 1984, 5 years after the accident. Video cameras lowered into the reactor vessel revealed that approximately 45% of the reactor core had been severely damaged, with fuel assemblies in the central and upper regions of the core reduced to debris beds rather than maintaining their original geometric configuration. The visual evidence confirmed that core damage had been far more extensive than initially estimated based on instrumentation available during the accident. Detailed forensic examination revealed that peak fuel temperatures had reached approximately 4,000 degrees in some regions of the core, approaching the melting point of uranium dioxide fuel pellets. Zircaloy fuel rod cladding had oxidized extensively due to steam zircaloy reactions at high temperatures, confirming that hydrogen generation had been substantial during the core uncovery period. Approximately 20 tons of core debris had relocated to the bottom of the reactor vessel, demonstrating that fuel geometry had been completely lost in severely damaged regions. The forensic evidence directly contradicted the information that had been available to operators through plant instrumentation during the accident. Pressurizer level indication, which had shown rising inventory throughout much of the accident progression, had provided systematically misleading information about actual core cooling adequacy. The instrument had functioned correctly from a measurement standpoint, accurately reflecting differential pressure across liquid columns in the pressurizer, but the physical conditions in the reactor vessel had invalidated the assumptions underlying interpretation of those measurements. Core exit thermocouple data, preserved in plant computer records, provided a detailed timeline of temperature progression during core uncovery. The thermocouples had accurately measured steam temperatures above the damaged fuel assemblies, but operators had not recognized these readings as evidence of core uncovery because training had not prepared them to interpret superheated conditions as indicating loss of liquid cooling. The instruments provided accurate information, but the interpretive framework for understanding that information under severe accident conditions had been inadequate. The Kyshtym Commission, appointed by President Carter to investigate the accident, concluded that the primary causes were human factors failures enabled by deficiencies in training, procedures, and control room design rather than fundamental nuclear technology problems. The Commission identified the pressurizer level indication issue as a critical factor that had led operators to make decisions that worsened the accident progression, while believing they were following correct procedures for post-trip recovery. The Nuclear Regulatory Commission's investigation reached similar conclusions, while emphasizing that the accident had resulted from a combination of equipment failures and human errors rather than a single root cause. The NRC analysis highlighted the role of inadequate emergency procedures that had not addressed complex multi-failure scenarios and the lack of instrumentation capable of providing direct indication of core cooling adequacy under severe accident conditions. The TMI-2 action plan, developed by the NRC in response to the accident, mandated fundamental changes in nuclear plant design, operation, and regulation. The plan required installation of direct core cooling monitoring instrumentation, including core exit thermocouples and reactor vessel level indication systems, to provide operators with better information about actual core conditions during accidents. These requirements addressed the instrumentation limitations that had contributed to operator confusion during the TMI-2 event. Emergency operating procedure development was revolutionized through the implementation of symptom-based procedures that responded to plant conditions rather than assumed initiating events. The new procedures emphasized maintaining critical safety functions, core cooling, heat removal, and containment integrity, regardless of the specific failures that might be occurring. This approach addressed the problem of multiple simultaneous failures that had not been adequately covered by event-based procedures. Control room design standards were modified to address human factors issues identified during the TMI-2 investigation. The new standards required better alarm prioritization, improved information display, and enhanced operator training on plant response during accident conditions. These changes reflected recognition that the human-machine interface had contributed significantly to operator errors during the accident sequence. Severe accident research programs, initiated as a direct result of TMI-2, developed new understanding of reactor physics and thermal hydraulics under conditions that exceeded the original design basis for commercial nuclear plants. This research confirmed that reactor designs included substantial safety margins even under severe accident conditions, but also identified scenarios where those margins could be challenged if accidents were not properly managed. The regulatory framework governing nuclear plant licensing was expanded to consider severe accidents that exceeded design basis assumptions. New requirements for severe accident management guidelines, enhanced emergency response capabilities, and improved coordination between plant operators and off-site authorities reflected lessons learned from the TMI-2 experience. These changes acknowledged that accidents could exceed design assumptions while remaining manageable through appropriate response strategies. Training programs throughout the nuclear industry were fundamentally restructured to emphasize understanding of plant physics and thermal hydraulics rather than rote procedure following. Simulator training was enhanced to include severe accident scenarios and emphasized the importance of monitoring multiple plant parameters to assess actual safety function performance. The training changes addressed the cognitive biases that had influenced TMI-2 operator decision-making. The 3 Mile Island accident demonstrated that nuclear plant safety depended not only on reliable equipment and comprehensive procedures, but also on operator understanding of the physical principles governing reactor behavior under abnormal conditions. The accident revealed systematic weaknesses in the assumptions underlying plant design, emergency procedures, and operator training that had created vulnerabilities to accident progression, despite multiple layers of engineered safety systems. International nuclear safety practices were also influenced by TMI-2, lessons learned, with regulatory authorities worldwide implementing similar improvements in instrumentation, procedures, and training. The accident provided a case study in how seemingly minor equipment failures could escalate into major accidents when combined with human factors vulnerabilities, leading to enhanced focus on integrated safety analysis rather than single failure assessments. The forensic investigation of 3 Mile Island Unit 2 ultimately confirmed that the accident progression had been driven by information system failures rather than fundamental technology failures. The reactor had not failed catastrophically. Engineered safety systems had prevented core melt-through and containment failure despite extensive fuel damage. However, the accident had demonstrated that information provided to operators could be technically accurate while remaining operationally misleading, leading to decisions that accelerated rather than prevented accident progression. The systematic lessons learned from TMI-2 established new paradigms for nuclear safety that emphasize defense in depth not only in engineered systems, but also in human factors, procedures, and regulatory oversight. The accident proved that nuclear safety required comprehensive understanding of system interactions under abnormal conditions rather than reliance on individual component reliability and procedure compliance. These insights fundamentally changed nuclear industry approaches to safety analysis, emergency preparedness, and operator training, establishing principles that continue to guide nuclear safety practices 4 decades after the accident occurred.